Hello everyone. In today's session, we'll be running the BLX instruction and we will see how exactly it works. In order to run this particular code, the target that we have chosen is NXP LPC2919 because it is made up of ARM 968ES CPU core, which in turn is based on ARM version 5 TE architecture. Let's first check if there are any errors here. Since there are no errors, we'll proceed to debugging. Okay, the first two instructions are simple move instructions which will load the value 3 into registers R0 and R1. Let's see that happening. This is the actual instruction which we need to understand, that is BLX followed by label of a subroutine. Okay, let's see what it is. First is nothing but label of this particular subroutine, which is written under the thumb assembler directive, okay, which clearly means these subroutines are written with thumb instruction set. These are the different bits of the CPSR register and our focus will be on the T bit shown here. Okay, we already know our initial code is nothing but ARM code, because of which T bit is initially set as 0. Subroutine getting called here actually belongs to thumb section, okay, that is known by the CPU through the instruction encoding itself. Okay, once that is known, CPU will set T bit to 1, okay, to indicate CPU execution state jumping from ARM to thumb. Okay, and other than that, the label first here has some address 1C. Okay, what this will do is nothing but it will update PC with the value 1C so that control jumps to this particular location. One more thing that happens is the address of this particular instruction LDR R3 comma equal to second, which is nothing but the next instruction in the sequence, that is updated in LR. Okay, what exactly is that address? It is nothing but this particular address, which is C. So LR will be updated with C, PC will be updated with 1C, and T bit will be set as 1 as soon as this particular instruction, that is BLX instruction, is executed. And immediately you will see that the control will be jumping to the instructions under the label first. Okay, let's see that happening. Okay, so if you notice, LR is C, PC is 1C, and T bit is set as 1 as expected. And you can see control has jumped here into the very first instruction under first. Okay, so what is noticed here? We are supposed to perform addition of R0 R1, store the result in R2, along with that update the CPSR register. Okay, so let's go ahead with that. What are our R0 R1 values? Those are nothing but 3 and 3. So the value 6 should be stored in R2. And what changes you will observe here? Actually, in this particular case, since the result is 6, N will be 0 because it's not a negative result. Z will be 0 because again result is not 0. C will be 0 because there is no carry generated here. And overflow is also 0 because any overflow is also not generated. Let's see that happening. And as you can see here, register R2 is updated. Next, what we observe here is BX followed by LR. This will do two tasks. One, setting the T bit. One more thing is updating LR content into PC. If you notice here, what is LR content? LR content is C. This value C will be updated in PC. Okay, that is one thing that will happen. And one more thing is this instruction will check the LSB bit of the LR. Okay, LSB bit, what is C in binary? 1100, and the higher bits will be 0. If you notice, the LSB bit is actually 0. What does that mean? It means while jumping back here, okay, to the address specified in LR, the CPU should jump back to ARM execution state, okay, because of which T bit, which is initially 1 here, okay, now becomes 0. Okay, let's see if that happens or not. You see, T bits have changed and PC is updated with whatever was previous content of LR. Okay, so now it has jumped back here, okay, because this was the address stored in LR. Next, what we have is nothing but LDR R3 comma equal to second, which is nothing but a pseudo instruction. The purpose of this instruction is to load the address of this particular label into the register R3, okay. But one thing we need to note here is this particular label of the subroutine actually belongs to thumb section, okay, and assembler will already notice it in advance, because of which it tries to convey this particular information to the CPU by updating the LSB bit of the address which is uploaded into R3. That is, if we check this particular instruction, okay, its address is actually 20 here. Okay, as we click on that particular instruction, we can see the address here, that is nothing but actually 20. But the assembler tries to convey the information to the CPU that this particular label belongs to the thumb section, okay, or marks the thumb section, because of which instead of loading the value 20 to R3, it stores this value plus 1, that is nothing but 21. So you'll notice a value 21 getting stored in the register R3. Let's see if that is true or not. Yes, but when actual instruction is encountered, that is BLX followed by R3, what you notice is 21 is not the address updated in PC. That is because in this 21, the actual address is 20. The last bit is set as 1, something like this. Okay. Only for the CPU to know whether the call is happening here, okay, to an ARM subroutine or a thumb subroutine. Once this particular value is seen, CPU understands, okay, now the call is happening to thumb subroutine, so it will make sure the address 20, that is, by clearing the LSB bit, the actual address itself is loaded into PC, okay, and the address of the next instruction, that is this particular instruction, is updated in LR. That address is nothing but 14, because of which address 14 will be updated in LR. Okay, so PC will get the value 20, LR will get the value of 14. Along with that, before clearing the value of the LSB bit and updating it into the PC, the CPU makes sure that the T bit here, okay, is changed back to 1 to indicate the subroutine we are jumping here is actually a thumb subroutine. Let's see that happening. Okay, so the jump has happened. T bit is changed. LR got the value 14 as expected. PC got the value 20 as expected. Okay, now we will come back here. The first instruction that is expected under the label second is nothing but subtraction. R0 minus R1 happens and the result is stored in R2. Along with that, CPSR is expected to be updated because of the yes here. Okay, so what should be the result? 3 minus 3 is 0, because of which obviously Z flag will be set as 1. In this subtraction, any borrow is not generated, because of which carry will be set as 1, but negative and overflow flag will be 0. Okay, so this is the first step which happens here. Okay, and the result 0 is stored here. So next what we have is the branch and exchange instruction. Fine, and what value is there in LR? If you notice here, value 14 is stored in LR. So as soon as this instruction is executed, this value is updated in PC so that the control jumps back to here. Okay, and other than that, what else happens? Because the LSB bit of LR is actually 0 in this particular case, that is, the value here is 14. 14 in binary is something like this. Last bit is actually 0, because of which there is a state change happening here from thumb execution state to arm execution state. Okay, let's see that happening. Okay, so it has jumped back here. We have seen PC getting updated and T bit changing. Okay, and finally we have a simple instruction which updates R2 S4. Okay, and this is an unconditional branch. Okay, these were a few things you needed to know about the BLX instruction.